Okay. So, so the question has like two scenarios, right? So the first one is the block with the vice, and then the second one is the block in a frictionless surface, right? One, you have the kinetic energy of the bullets, VB squared. Okay, we'll begin with like the energy of conservation. So you could use momentum, but then the professor said like it doesn't make sense. Do you remember why?
For this question?
For the first part, when the block is in the vice, do you know why it doesn't work? The momentum equation? No. Okay, well,
I thought it would.
no, because look, if it's the mass of the bullet, velocity of the bullet plus the mass of the block and the velocity of the block, initially it's zero, so we can cancel that out. And then finally you'd have just the mass of the block and the velocity of the block, right? And then because the bullet would be stationary now, because it's lodged into the block of wood.
Yeah.
This wouldn't work because one, I mean, like mathematically it wouldn't work because the velocity of the block doesn't change, it doesn't increase,
Okay.
right? Because it's like completely stationary in the vice, so it doesn't move at all.
Yeah.
So here you're saying that mvb equals to zero, but that makes no sense, right?
Okay.
So the entire equation just breaks apart. It doesn't work because your object is stationary.
Mm.
It won't work the momentum because even though it's conserved, the change in the velocity is so small that you can't measure it,
Okay.
right? So you have to use the energy equations. So you know that the initial and the final energies are the same. Okay, and then I'll give you have the initial kinetic energy of the bullet, right? That makes sense. And then the final energy, since it doesn't move at all, you need to see where the energy went, right? So if the bullet gets fully lodged into the block of wood,
Yeah.
the energy was lost somewhere, right? So we can say that energy was like negative work done to the block.
Okay.
Does that make sense?
Yeah.
So the block of wood didn't work on that bullet, so it becomes like stationary, right?
Mm.
And then we can say that that work is equal to some force times the depth it got through,
So you have 1/2 mv squared
right?
is equal to the work.
The work, right?
Okay.
And then the work is equal to some amount of force that the block of wood gave to the bullet times the distance that traveled from. So like that depth it went into,
Yeah.
which we know, right?
So FT cos theta.
Uh, but cos theta is
One.
yeah, because it's the horizontal, right?
Zero.
So FT,
Okay.
right? So then here we have 1/2 mv squared is equal to FD, right? You can label this force. The professor called it force friction because it's somewhat like a force, like a frictional force, but it's not really. So you can just leave it as FD, right? It doesn't matter to you if you label it or not, okay? So with this equation, you can't actually do anything. We'll label this equation 1 because we'll use it later.
Okay.
Right.
So just say FD is equal to 1/2 mv squared.
Yeah.
And you know liquids. M is it like okay, sorry, no. Okay. Equation. All right.
Cool. Now for the second problem, because we're on a frictionless surface, the block can move, so momentum can be measured. Does that make sense? Because once the bullet actually hits the block,
Mm-hmm.
the block is free to move,
Yeah.
right? So that means our initial momentum is the mass of the bullet, the velocity of the bullet, plus the mass of the block and the velocity of the block. We know initially the block isn't moving at all, it's stationary, so that becomes zero, right? And then in the end, we have the total mass times the total velocity, right? And we'll call that like V.
Okay.
Does that make sense?
Yeah.
V total. Does that make sense? Because it's an inelastic, elastic collision.
So
Inelastic, sorry.
for the first equation you have, what mass and velocity is that?
The bullet. So we'll actually label that too. So this is the mass of the bullet and the velocity of the bullet,
Okay.
right?
So you have the mass of the bullet, times velocity of the bullet,
Right?
plus mass of the
Block.
block
Yeah.
times velocity of the block,
Yeah,
which
but
is not zero. is 0.
initially for the second scenario
Okay.
when the box is free to move,
Okay.
right?
So then you have that equal to
To the total mass of the entire system times the total velocity of the entire system.
would it not be mass and velocity of the bullet after plus mass and velocity of the block after?
Because it's an inelastic collision, they'll become one block, so they have a combined velocity.
So then don't you have to separate their masses?
Yeah, I'll do that after. Like here. So now I'm going to say that the total mass is the mass of the block plus 2 of the mass of the bullet. Because we have one bullet from the previous hit,
Yeah.
and now there's a new bullet. That makes sense?
Okay.
Like that, does that make sense?
Yeah.
Because we have that initial bullet, it's still lodged in there. We're shooting at the same block.
Yeah.
And we have the mass of the block itself, and then this new bullet. And since it's an inelastic collision, they move together, right? So they have a combined velocity.
Yeah.
And that's all equal to the mass of the bullet and then the velocity of the bullet.
So
Right?
for this part, would it be? Oh, so that's a block. That's a block.
Yeah, the mass of the block. Capital F.
You have. Wait, so you said this is an inelastic collision.
I mean, it has to be. How can it be elastic? Like, how would the bullet bounce off of the
How do you picture elastic collision?
elastic? Only happens when the energy can be directly transferred back.
Yeah.
So if you have like springs, like it only happens with like springs and spring-like objects, right? So like a puck and a wall would hit, and it would bounce out. It wouldn't become the same thing, right? Like puck wouldn't go so fast; it becomes one with the wall, right?
Yeah.
So some things do bounce off with some energy,
Yeah.
but most things do not. So with the bullet, like even without understanding collisions, you know that the bullet gets lodged in, right?
Yeah.
So how can the bullet get lodged in and then push itself out?
So like if it can reverse its process?
Like could it? Like could the no right, it can't because it gets stuck inside the block, right? So that's why we know it's inelastic. They become one unified object.
Like sticks together.
Yeah, exactly. That's what it is. They stick together. Inelastic collisions mean they stick together.
Okay.
Right?
Yeah.
That makes sense?
Yeah.
Okay, now with this new equation, we can't really do much. So we'll label this equation 2. And then we'll create another final equation. And this would be using energy again. So the energy initial and the energy final are the same. Right? So initially we have again the kinetic energy of the bullet. And then in the end we have the 1/2 the total mass of the bullet and the total velocity. I mean the block, sorry.
Okay.
Right? That should be right. Yeah. Right, that makes sense? Because they're moving both now together. Does that make sense?
Yeah.
Right? Does that make sense too?
Yes.
Because initially the block wasn't moving. Now the block is moving along with the bullets because they're one object. So then if we can expand this out, it'd be 1/2.
So then would it be like the velocity of the block plus the velocity of the bullet? For the final energy?
For the final energy.
And their masses as
Well,
well?
the velocity of the block is 0 initially because it's stationary.
But I mean for final.
Final would be 0 plus the velocity of the bullet.
I'm asking, I don't know.
Not fully, no. I mean, the velocity may be maintained, but like it won't have the same like magnitude.
Yeah.
Like because let's say a bullet of like 50 grams is moving at like 500 kilometers per hour. If you hit something massive, it won't push that block at 500 kilometers per hour, right?
Yeah.
So it'll lose some energy because of the collision, but it'll still travel at some velocity.
Okay.
So that's why we don't denote it as the total velocity.
Yeah.
Right. And then the total mass is again the mass of the block plus 2 masses of the bullet. V total squared, right?
Okay.
And we can also cancel out the 1/2. So MV EB squared, right? That makes sense?
Right.
The 1/2 just cancel out.
Oh, okay. Okay.
And you can expand out the total mass, right?
Expand, how do you?
Like expand, so I wrote here MT or M total.
Okay.
That's the same as the mass of the block plus the 2 bullets.
Yeah, yeah.
Cool. So now we'll label this final one as equation 3. And then now we can say that we want to find the depth to which it goes in. Oh, sorry, wait, that's wrong. I'm so sorry. I misled you. My bad.
Wait, what we just did is wrong?
Yeah. Well, no, it's not wrong. It's just the wrong approach. Like, it's the wrong equation we're considering. I delete it. Okay, wait. Let me see what I did before. It's the right. Okay. So here, no, okay, what we did was right. It's just partially incorrect. I forgot one thing. So we do actually end up with 1/2 the mass total times the velocity total squared, right? But we also have something else. Just like the first collision, we had some work done against the bullet. We have the same thing here. So we have the work done on the bullet. And we know that's the same as the sum force times the distance, right? Does that make sense?
Yeah.
So this is the same as mass bullet plus 2m bullet, velocity total squared, plus some force, and then we'll call this one d prime actually, just to say that it's a different distance that it travels. Does that make sense?
Yeah. So you have M1, M1 V1, in that case, MV1 is equal to massive 2 primes times v squared. Where did you get FD from?
FD, so that's the work, right?
Why are
So-
you adding work?
So on top of the bullet giving some energy to the block,
Yeah.
some work or energy was also lost because, like, the first one, because it was in the vise, all the energy went towards the work being lost, right?
Yeah.
That makes sense? Because it can't lose work any other or energy in any other way because it's stationary, like
Yeah.
it can't move at all. This one, it's free to move, so in the end, it'll have some movement, so that's some kinetic energy, plus the work from that collision, right? And that work we defined as FD before as well. So this is the same thing, but this time the distance it happens, like the depth it penetrates the block, is different. So we'll call it d prime for that
Yeah.
reason. That makes sense?
Okay.
And then now we actually have our third equation. Cool?
Okay.
Now, what we can do is take the first equation.
This is a crazy question.
I know it's pretty crazy. And then divided by. Actually, no, we're going to do the other way around. Okay, so what we're going to do is take the third equation, modify it a bit, so that's why I have the prime there, and then divide it by the first equation.
Okay.
Right? And what I mean by modify is that I'll isolate for FD.
Okay.
Cool. So that means we'll have FD prime over,
But you're isolating for FT or FT prime?
well, both the work terms, if you want to call it.
Mm.
Both the work terms on both equations. Right? So we'll here, on the top, we'll have 1/2 mass of the bullet, velocity of the bullet squared, minus 1/2 the mass of the block, plus 2 times the mass of the bullet, times the total velocity squared, right?
Mm-hmm.
And then on the bottom,
You just cancel out the 1/2 on both sides, right?
if you'd like to, you can. Oh, no, you can't, because we have the FD.
Okay.
But you can factor it out if you want to do that. Now here you can, on the bottom, you'll have 1/2 mass of the bullet, velocity of the bullet squared, right? All right, now, if we continue working on this, things just cancel out. So we see here that this term and this term are the same. Do you see that?
Yeah. So that just goes.
Becomes 1,
Okay.
and then it's minus, and then we can see that we have a 1/2 here to 1/2 here. So those cancel out. So then you have the mass of the block plus 2 times the mass of the bullet times the total velocity squared, right? Over the mass of the block times the velocity of the bullet squared.
Okay.
Does that make sense?
Yes.
Like, do you see how I got there?
Yeah.
Cool. Okay, now I'm going to rearrange it a bit more. So here I get the velocity of the total velocity, the velocity of the bullet. Then we're squaring both of these terms times mass block m block over m block. That makes sense?
Yeah.
Cool. Okay, now we're going to simplify one more time. Now we get 1, and then here we get that it's 2 plus mv over mb. Do you see how I did that? Because these guys cancel out.
Okay.
These two. Okay. And then we again have velocity total VB squared. Right? And then of course this is
FD primed over FD.
yeah. But then here we can also write that as D prime over D. Because these two forces, these two random forces, irregardless of
They're the same.
yeah.
Okay.
You assume they're the same. Regardless of what you know about them. Right? There?
Okay. So you have D prime. So you have D prime is equal to brackets 1 minus 2 plus m massive block. You're gonna rewrite the massive block as 2.
No, massive block is just massive block. I already expanded everything out.
Okay.
Yep. 2 plus mass of the block over mass of the bullet. Does that make sense? How I got to here?
Yes. What's V? Is that V? What is that?
V total.
What's this? V1?
Sorry, V total. That's a T.
What do you mean total?
V total is every single time it collides inelastically, the final velocity is the combined velocity of the entire object. So we write that as VT.
Okay.
Cool?
So I can just write kind of V block plus V.
It's not necessarily that. That's the thing. You don't know if it's that.
Okay.
Right? Like the example I said, like
Yeah.
if a bullet hits a block, it won't travel at the same velocity. So here we would be done, but we don't know the velocity total or the velocity of the bullet, right?
That's velocity bullet, right?
Yeah, VB. And that's velocity total. We don't know either of those.
Why do you is it squared?
Yeah.
Okay, yeah. So we don't know those.
Cool. But we have another equation we didn't use, and that's equation 2,
Okay.
right? So now we can label this equation, I don't know, let's say 4. So basically we put equation 4 and equation 2 together.
Okay.
Right?
To get rid of V total.
VT and VB. Because we have VT and VB in our equation 2.
Okay, yeah.
Cool. So we get that D prime is equal to D times 1 minus 2 plus MB over MB times here we can actually rearrange it here. VT over VB so we equal to M bullet over mass of the block plus 2 M block. Right?
Mm.
You understand how I did that?
Mm-hmm.
Cool. So now we can plug it back into here. So we get the mass of the bullet over mass of the block plus mass of the bullet. And of course all that's squared. Cool. So here we could just like evaluate if you wanted to. But I'm gonna like undo something I did before. Wrote this wrong. Okay. Do you understand how I got to here? So from here you can evaluate, right? But I'm gonna do something to make it simpler.
Simpler?
Yeah. Like a simpler equation.
Okay.
Like the ultimate equation.
So
Right?
I don't believe you, but
Why?
ultimate equation.
No, it's much simpler.
Nice and hard.
Because look, do you remember when we simplify this term right here.
No. Yes.
Yeah. So let's unsimplify it.
Unsimplified.
Like undo what we did. So this
Okay.
would be 2m bullet plus mv over mb, right? And then the next term is mass bullet over mb plus 2mb. And of course it's squared. Now what we can see is that a bunch of things cancel out. So this first square cancels out, this cancels out, this cancels out. Oh, not really fully, but this and that makes sense?
How does the square cancel out?
Because you have this would be mb squared. So mb squared over mb is just mb. Right?
Okay.
So then you get d times 1 minus mb over mb plus 2. Cool.
Okay.
And that's your final equation. d1 prime. Alright, d prime.
Okay. And you plug in the numbers.
And then you can just plug the numbers in here and you get it.
This was a crazy question.
What's
Were you recording, by the way?
I was.
I'm sorry.
Wait, why?
Because I talked a lot.
No, that's good though. So then the viewers know. Okay. Does that make sense though?
Yes.
Like you could do that on your own on a test?
No,
Come on.
not yet. I'll have to practice it, but it definitely helps.
Good.
Uh,
Well, you'll have the video for later, so.
True.
Alright, cool.